Hey you guys, I am recording this video for fourth block because I am in a meeting, and so I wanted you guys to get the same lesson that first block got. If you're not here today, then this is also the same lesson first block got. But I need everybody to just be able to get this, so I'm recording it for all of you. This is a pretty simple lesson. It'll be the first lesson in our new unit on solving systems of equations and inequalities. And a lot of what we do in this lesson is Desmos related. So hopefully after you watch this video, you'll have a better understanding of how to use Desmos to help you solve systems of equations and inequalities. And then we'll go from here tomorrow into looking at how to solve systems of equations and inequalities with algebraic methods other than graphing. So by the end of today's lesson, you should be able to graph a system of equations or inequalities to determine the solution. You should also be able to tell the number of solutions using that graph. So most of what we do today is going to be kind of flipping back and forth from Desmos to our slides and back. So there'll be some times when I ask you to stop and try some of these things in Desmos. There'll be other times that I just show you what you will use Desmos to do for these particular types of questions. So we'll kind of flip back and forth between that. We will finish these slides and be able to submit them today, so it looks like maybe a long lesson, but it really is pretty simple. So it should not take us too terribly long to get done. So I want you to think for a minute about linear equations. We did linear equations last 9 weeks, and we looked at how to find the solution to a linear equation when graphing it. And so we looked at how we could graph a y equals mx plus b equation and use that to identify solutions. Now think about if you looked at that in Desmos, and I'm going to show this real quick. Oops, just kidding. So if I were to graph that y equals 3x plus 4, remember, when you graph a linear equation like that, it brings up this line. And hopefully you remember that the way we found solutions to that was we picked any point that existed on the line. So this point at 0, 4 works, this point down here works. But also any of these other points that were on the line were considered solutions to that equation. So anything that exists on the line is a solution to a linear equation. And so we're going to add that in here. So when given a linear equation, how do we identify solutions? Graph it. And choose any point, or any points, because it can be many of them, that are on the line. And look, I know that it makes that tapping noise when I write with my Apple Pen on this screen, but I don't really know what else to do with that, so I apologize for the tap, tap, tapping if it's driving you crazy. I may try this with a regular stylus instead. But anyway, any point that is on the line is going to be a point that would be a solution to that. So now we're going to look at a system of equations. So a system of equations means we're looking at more than one equation together that have to both be true in order to create a solution for that. So just like a skeletal system is made up of multiple bones, or an exhaust system in a car is made up of multiple parts, we've got a system of equations that's made up of multiple equations together that have to be solved in order to give a solution to that system. So a system of equations is a set of two or more equations with two variables. Yeah, this is way better. It doesn't tap. Can't write quite as small, but it works. So two or more equations with two variables. The solution to that system is an ordered pair. So just like solutions to single linear equations are ordered pairs, the solution to a system is also an ordered pair. So it's an x comma y. Yes, it needs to be an x and a y together with a comma, parentheses on the outside. The solution that you get to a system represents the point where the lines intersect. So you're going to have more than one line. You're finding the point where those lines intersect each other, cross each other. The xy at that point is the value that makes both equations true. at the same time. I thought I was erasing that. So that's what we're looking for when we're looking for the solution to a system. We can graph it in Desmos. We can look for that point where those lines intersect. And that point's going to tell me a solution that would make both equations true at once. Let's look at the types of solutions. So maybe you remember a long time ago when we solved equations. And we could get 3 different types of solutions. If you remember when we got an equation that was like, don't write this down, but just think about it. 4x plus 2 equaled 2x plus 1. When the x part was different and the b was whatever, there was one solution to that. And then we could do one that was like 4x plus 2 equals 4x plus 3. And there was no solution because the x's were the same and the b's were different. And if everything was the same, it was infinite. Well, we have a similar situation with this system of equations stuff, where we could have one solution, we can have no solution, we can have an infinite number of solutions. So let's look at what that looks like. We have one solution, we have no solution, and we have an infinite number of solutions. So one solution, remember the solution to the system is the point where the lines intersect. So you have a system with one solution if the lines cross once. So that's going to look like this. Maybe. Oh, just kidding. Oh, yeah, that worked. That was beautiful. All right, so if I have a line that way, and then I'm learning how to work this, y'all, so I apologize. And then I have another line going like this. That's going to be a system that has one solution because they have a single point of intersection. And that point of intersection is the solution to that. Now, if one solution means they cross once, to have no solution has to be a situation where the lines never cross. So you got to think, what kind of lines never cross? The only kind of lines that never cross are parallel lines. And I need you to know that word, that parallel means there's no solution, because it's very, very likely when you guys take your state test that pops up. They'll say what kind of equations have no solutions, and you got to be able to pick out that parallel lines would have no solution. So that's going to be a situation that looks like this. And I probably won't draw this very well, but we'll hope for the best. So 2 lines that don't touch are parallel. There's no solution to that. And then to have infinite number of solutions means everything is a solution. Has to be a situation where the lines are exactly the same. So if our lines, when we graph them, come out to be in exactly the same spot. So I'll graph one right here. I'll graph a second one directly on top of it. That didn't work out so well. Try again. Where those lines are exactly the same thing. And maybe yours will look better than mine. Mine's a little wonky. That's a little bit better. Then you know there's a situation of infinite solutions. And it'll be very obvious in Desmos if you graph it that there's an infinite number of solutions or that they're the exact same line. I don't know what I just did, y'all. I apologize. Hold on. Okay. Anyway, so that's what we're looking at with that. So if we have a point of intersection that they cross once, there's one solution. If they don't cross, there's no solution. If they cross everywhere, it's infinite. So let's look at how we do this. So if you're going to solve a system by graphing, and again, I'm going to show you some other options on how to solve systems other than graphing, but this is the easiest method, and it'll be the one that you probably are going to use as a go-to for most problems because Desmos is available to you on the state test. But basically, you're going to use Desmos to create a graph of both lines. You're going to locate that point of intersection. And you're going to write the answer as an x comma y. So you have to give your answer as an ordered pair. It cannot be just a single number. It has to be an x and a y. If you don't put it in parentheses, you'll be wrong. So you want to be careful with stuff like that. All right. So let's look at some examples of this. And I'm going to work these first two with you right here. And I'm going to pull Desmos up and we'll work them and talk about what we get. And then we'll do a couple more like that. And then we'll kind of go from there. So you can pull Desmos up if you want to. You don't have to because I think you can probably see it pretty well from what I'm showing you right here. But if you want to pull it up because you prefer to do that, that's totally fine. So if I graph this system, what I'm going to do is I'm going to graph both equations at the exact same time. So y equals negative 2x plus 3. Oops. And really the only way to mess this up is to mistype what you're graphing. So that's got the first one. Now I'm going to go and graph the second one on the second line. Y equals 3x minus 2. Okay, and so what I have here is my system of equations. It's been graphed. I look at the shape of that graph first to even determine if there is a solution or not. Now we see that these lines intersect one time. They cross each other. So there is a solution to this. So to find that solution, I'm just going to find that point where they intersect. Now something you want to be careful of is if I'm zoomed way out and I'm trying to find my point of intersection, sometimes there's going to be more than one point down here and it's going to be hard to tell which one is the point of intersection. So if you're zoomed out, you want to make sure you zoom back to a normal range so that you can really see well. But the point of intersection is going to be this dot where those two lines cross each other. Not this dot down here on the axis, not this dot up here, not this dot or this one. There's a lot of different dots that they'll show us. We're only interested in the one where the lines intersect each other. So I want that dot in the middle. And hide both of those. And so my point of intersection is 1, 1. That means the solution to this system of inequalities is 1, 1. I'm going to write that exactly like that, 1, 1. And what that basically means is if I put that x value that's right here in for x in both of these and calculate it, I would get the y value at 1. Because 3 times 1 is 1, minus 2 is 1. And negative 2 times 1 is negative 2, plus 3 is also 1. So I basically have a single point that makes both equations true at the same time. Now let's look at this other one. So I'm going to do the same thing. And I'm going to graph 3x and then 3x minus 2. Hang on. Move. So y equals 3x. And again, really, the only way to mess this up is to graph it wrong. And y equals 3x minus 2. So look at those. We're looking for where they intersect each other. And if I keep going this way for a long, long time, they never cross that way. If I keep going this way for a long, long time, they never cross that way. Now, if I pinch and zoom out, they almost look like they're the same line. We got to be real careful about that because when you're zoomed way out, sometimes things look a lot different. But if I'll go back to my normal range, I know they're not the same line, but I can also see that they're parallel. And so since they're parallel, I know that they are going to have no solution to that system. So parallel lines have no solution. So these have no solution. And that's exactly what you'll write, no solution. You could also see the little circle with a line through it. That means the empty set or no solution. On your graded practice assignment, when you get no solution, they make you type DNE for does not exist. So if you see that, that's also no solution. All right, let's look at another one. Oh, I did not mean to do that. Okay, so I'm going to do the same thing here. Pull it up in Desmos. And I'm going to type them in. 2x plus y equals 3. And then y equals x plus 3. And so I see that these definitely intersect each other. I can see that they cross. That point where they cross is that point right there in the middle at 0, 3. So my solution, 0, 3. All right, let's look at the last one on this slide. So this one, 2x minus y equals 2. So again, I'm just going to graph it. And then 2 times x minus 1, y equals 2 x minus 1. Okay, so I graphed that. Now I only see the blue line. Keep zooming out, and I'm still only seeing the blue line, right? So obviously something strange is going on here. So things I want to look for. Number one, make sure you don't have like a caution sign on one of these two saying that you've typed something wrong, because that's possible. But since I don't, I'm going to hide the blue one and see if I can find where the red one is at. And if I do that, notice the red one suddenly shows up, because the red and the blue were in the same spot and blue was laying on top of the red. So those are actually the exact same line. And so since they're exactly the same line, I know that this has an infinite number of solutions. So since they're the same line, this is infinite. You can also see that written with the infinity symbol. All right. So I want you to take a second and try these two with your group. So, or if you're at home by yourself, obviously. But if you will, just take a minute, look at these two, put them in Desmos, graph them, and then see if you can come up with a solution for each one of these. If you're my substitute and you're playing this video for everyone, if you'll pause the video right here, give them just a few minutes to work through this one, and then start the video back up. I'll pick back up with the correct answers to these. But give them a little bit of time to work these two out before you continue playing the video. All right, so hopefully you've had a chance to work both of those out. The first one, you should have gotten a solution of 1, -4. And again, we get that just by graphing that and looking at the point where they intersect. The second one, when you graphed it, comes out to be 2 parallel lines. So this one would have been no solution. So you wrote no solution, or you wrote 0 with a line through it to show that it's an empty set. All right, hopefully you were able to get both of those correct. That's really all there is to solving systems of equations with graphing. That's what we're looking for, that point where the lines intersect each other. So now let's look at systems of inequalities. So think back to when we did linear inequalities last semester, or last 9 weeks. And I asked you to identify solutions to that. So if you had something like 2x plus 4y is less than 5, let's look at what that looked like. Plus 4y. So if we had that, and I asked you to identify points that were a part of the solution, how did you know what to pick? All right, hopefully in your mind, or maybe out loud even, you're saying points that are in that shaded area. And that's exactly right. If you remember, anything that showed up over here in this shaded area was considered a part of the solution. Anything that was up here in the area that was not shaded was not. And then we have these lines. If we had a dashed line, we knew that points along that line were not in the solution. And we know if we had a solid line, that means we have the equal to bar to go with it. So that would be like this scenario. Then the solid line points are a part of the solution. So if you had a solid line, it was. If you had a dashed line, it was not. So to answer this question, when considering a linear inequality, how can you identify solutions? Choose any points in the shaded area on the solid line. So systems of inequalities basically work the same way, but now instead of having one shaded area, we're going to have two. And so we have to figure out points that fall in the shaded area for both. Anything that falls in the shaded area for both can be a solution to a system of inequalities. So, a system of inequalities is a set of two or more inequalities in two variables that must both be satisfied at the same time. So, to make a system, or unlike a system of equations, unlike a system of equations, a system of inequalities has many solutions. So a system of equations, if there is a solution, has one. A system of inequalities has a whole lot of different things you could choose that would be part of the solution to that. So the solution to a system of inequalities represents all points which lie in the solution set of both inequalities at the same time. The only way we solve a system of inequalities is by graphing. So, a couple of things we need to know about the solutions to a system of inequalities. So we're not going to have really situations of one solution, no solution, infinite solutions anymore. Although it is possible to have no solution. If nothing overlaps, there could be no solution to that. But majority of them are going to have a solution. So what we need to know, points in the double shaded, that's the part that's shaded in two colors. And we'll look at that in a minute. Portion of the graph are solutions to the system. Points on a dashed line are never solutions to the system. So if it touches a dashed line, it's a no. Now, with a solid line, with a system of equations, it's a little bit different. But points on a solid line that borders the solution area, and we'll look at what that means in a minute, are solutions. Points on a solid line that do not, or does not, the solid line does not border the solution area are not solutions. I think I muted myself, sorry. Are not solutions. All right. So let's look at what this means in terms of what one of these problems might look like. So if we were looking at this graph, and I wanted you to tell me some points that were in the solution set. We're just going to mark some of these, y'all. Some things that could be in the solution set would be any point that's over here. Now notice this. What we have is we've got this blue dotted line, and this area over here was shaded blue for that inequality. Then we have this red solid line, and this area over here was shaded red for that inequality. So the part that represents the solution set is anything that shows up in this area that's shaded in 2 colors. So all this over here would be points in the solution set. And anything that goes beyond there off the graph, if we could continue the graph out that way, anything that goes further this way would be part of the solution set. So if we're identifying points that are in the solution set, we can identify things like this point right here at 2, 0. Let's put a mark right there, label it A. Actually, let's just do it like this. This might be the easiest thing to do. Pick green. If you're not writing in green, change your color to green. And we'll put green dots to represent things that are in the solution set. And we'll use red dots to represent things that are not. Green means go. So green dots mean things that are. Red dots are things that are not. So a green dot in any point over here in the solution set would be anything that's in that double shaded area. Now I could also put a green dot on a point on the solid line as long as that point is in the border of the solution set. So if this is the solution set, a point along this solid line right here would be okay. A point down here would not. So even though the line is still solid, this does not border my solution. So this is not a part of the solution set. But anything on this line would be okay. So I'm going to put another dot right here. Or you could put one up here. Anywhere along that line would be good. You also could have one that's not on an axis or on a line. You could have just some random point out here in Neverland. Anything that's in that area would be a part of the solution. Now, points on that dashed line that's along the border, those are not a part of the solution because that line is dotted. So I'm going to draw a red dot right there. That's not in the solution. Other points that are not in the solution would be things that are only shaded in one color. Or something on the solid line that's not in the solid line, not in the boundary. Let me erase that and fix it. I accidentally switched slides. I don't know if y'all can tell that or not, but anyway. So like that. And then anything, of course, out here in the middle of the non-shaded area altogether, that would all be things that are not in the solution. One other thing that comes up a lot is what about the point of intersection for the 2 lines? So that's this point right here. Because this point exists where a dashed line is, this point is not in the solution set. If this line were solid instead and these 2 solid lines intersected right there, it would be fine. But because there's not, it's a dashed line, that's not considered a part of the solution. So I'm going to put a red dot right there for this example. So in this, we've only shown really 3 points that are solutions, and all these different scenarios that are not. So we want to make sure we know exactly what we're looking for there. We're only looking for points that are in that area that's shaded twice, or follow along a solid line that borders that area. So points along here. All right. Boundary. So let's look at an example of this. And so we're going to actually graph these 2 inequalities and show the solution set on this graph here. We're going to use Desmos to help us do it. So I'm going to pull Desmos up. And I'm going to graph those. So y is less than or equal to negative x minus 2. Negative x minus 2. And then y is greater than or equal to negative 5x plus 2. I don't know what just happened, but okay. Okay, so I've graphed this system of inequalities right here. And what I can see from it is that it creates for me two different lines. I've got one red and one green. They intersect right here. That point of intersection is not necessarily important to me at this moment. But what is important to me is that I recognize the area of this that is shaded in two colors. So if you notice, I've got this area shaded in red, this area shaded in green, and this area here is shaded in both. So this little area right here is actually what represents my solution set. Now, if you're asked to create a graph to represent the solution set for a system of inequalities, you're going to have to graph both lines and shade both inequalities so that you can show the part of the shading that overlaps. The easiest way to do that is to hide one of your inequalities in, let me hit the right button, in Desmos, hide it. And then just graph the other one by picking 2 points off that line that you can graph. Now this one, I happen to be able to pick the points on the axis because they're nice, pretty points. So I can put a dot at -2, 0, and a dot at 0, -2, and I can form that line. So I'm going to come back over here, and I'm going to do that. So I'm going to put a dot at -2, 0, and I'm going to put a dot at 0, -2, and then I'm going to draw a line between those 2 points. Now the line was solid in Desmos, so I'm going to draw a solid line here. And you really want your line to extend the whole length of it. I just can't actually draw that without drawing it and then fixing it. Should do something like that. So I picked 2 points and then I drew my line through the whole graph through those 2 points. And then it's shaded, if you remember this one, shaded under that line. So I'm going to come back, shade that area that's below the line. It doesn't have to be beautiful. But that creates the first one for me. So again, I did that by picking 2 points off the graph. And I could have picked any points. I didn't have to pick those 2 on the axis. I did pick those because they showed up and they were easy. But you could have picked any 2 points on that line, and they would have worked. So just because I picked those 2 doesn't mean those are the 2 you had to pick. But I picked those points and then I shade in the correct direction. So now I'm going to hide that one and bring my other one up, and I'm going to draw it. So it goes through 0, 2, and then it goes through the other point over here at 0.4. I can't really use that because I'm going to be kind of guessing where that's at. So I'm going to look for another whole number point. And so the next one I come to is down here at 1, -3. And so you can kind of see that right here, 1, -3. So I'm going to put a dot at 0, 2, and I'm going to put another dot at 1, -3. And I'm going to connect those with a solid line because this line is solid. So I'm going to go 0, 2, 1, -3. And I'm going to draw a solid line between them. And this one's shaded over to the right side of that line. So I'm going to get my highlighter. I'm going to shade to the right. And again, it doesn't have to be pretty. It can be out of lines. It doesn't matter. And so I end up with that. And so I know that my solution to this represents anything that falls in that double shaded area. If I still have people working on this, y'all can pause this video and finish creating that before you move on to the next one. Oops. All right, let's do one more of these. So again, I'm going to bring up Desmos. I'm going to graph this. And this is actually the same ones that we graphed on the last one. So y is less than but different signs. Negative x minus 2. And, oh, I said less than, but it's greater than. Y is, my keyboard's kind of being delayed here, y'all. Less than negative 5x plus 2. All right, so for this one, we're going to do the same thing. We're going to graph it with 2 different lines, shading 2 different times. And then we're going to look for points in the area that is shaded twice. So if I'm going to graph the first one, I'm going to hide the second one so I can just look at the first one, find 2 points. So I can graph negative 2, 0, and 0, negative 2 again. This time, notice my line is dashed. So when I graph this, I'm going to want to make sure to use a dashed line to do that. So 0, negative 2, and negative 2, 0. I said that backwards. Negative 2, 0, and 0, negative 2. Same thing. So I'm going to graph that line. I cannot make a dashed line on here, unfortunately. So what I'll do instead is this. I'm going to graph a solid line, then I'm going to come back and cover up some parts of it. So I don't know how you want to handle that. You may want to graph it as a dashed line. From the beginning, but I'm going to go with it something like this. If I can get my line lined up correctly. Okay, so like that. And then it's shaded above it this time. And I know that because I can look and I see my line and it's shaded to that side. So I'm going to shade above. Actually, let me fix my thing first. I was hoping it would let me erase part of that. It doesn't. Okay, well, let's do something different then. Can I change my color? Yes, I can. Okay. So I'm just going to go and erase some parts of that. Oh, it's not ideal, but it'll do. Whatever it takes to make it look dashed, because that's what we need. I actually really don't like the way that looks, but anyway. All right, so something like that. And then I'll shade to this side of it. All right, and then I go back and I graph the other one the same way I did that one. So I'm going to hide the first one, bring up the second one. Again, I got to find 2 points. So that point at 0, 2 works. That point at 0.4, 0 doesn't. So I'm going to come back to that same point I used last time at 1, negative 3. Again, I've got a dash line for this one, and I'm going to shade to the left side of it when I get it in place. So a dot at 0, 2. A dot at 1, negative 3. A dashed line. Same deal, I gotta go back and dash it. So, not perfect, but it'll do for this. And then to show everything on the left side of that, I'm going to grab that highlighter and I'm going to shade everything on this side. So again, the part of that represents my solution is the part that's in the part that's shaded twice. All right, now that we've created some graphs of that, and again, if you need a little more time, you can pause the video and finish that up before you move on. But now that we know how to create that solution set and choose a graph that matches, now let's look at some questions that will look like what this might look like if it were tested. So here we have some examples of problems asking you which ordered pair would be in the solution set for a particular system of inequalities. So this is a situation where going to Desmos and graphing it, and then graphing your points is going to be your easiest option. So if I go to Desmos and I graph y is less than 1/2 x plus 4. And then I go and also graph y is greater than or equal to negative x plus 1. So I see this graph that I've just created. I see that I have an area shaded in red, an area shaded in blue, and this is the section that's shaded in both colors. And if you don't see that very well with the red and the blue, you can always change those to some different colors. But that's the part that's shaded in 2 colors. I have a dashed line up here on the boundary. I have a solid line down here. So when I go to look at these and evaluate these points, I want to make sure I pick a point that shows up in that area that is shaded twice, or in the area that is on the solid line that is the boundary. So I'm just checking all these points. 3, -5, and 4, 0. So when I look at all those points I just graphed, I've got a point here completely outside of the area. I have a point down here that's only shaded one color. I have a point here on a dashed line, and I have a point here on the axis in that area over here. The only one of these 4 points that is in the solution set is this red one. This one, because it's on a dashed line, does not count. These are not in the area that's shaded twice, so they don't count. So only that red one, that point at 4, 0, is my solution to this. So this is our solution. Now this next one's already been graphed for us. They just want us to pick the point that is in the solution set. Now sometimes you'll see one like this that's been graphed, but they don't necessarily graph it in color because a lot of times, especially if it's a black and white printed test, it's really hard to see the differences in the colors. But they'll shade it in 2 different patterns. So you've got a pattern of things shaded vertically, well, not really vertically, but kind of slanted this way over here, and a pattern of things slanted this way over here. So you can see where they slant together in this area down here. So when we check for these points, we're going to be looking for points that exist along here or along this solid line. So I'm just going to graph my points to see. My point at 1, 4, I'd go from the origin right 1 down 4, would put me right about there. That one looks good. That's in that area. But let's check the other ones to make sure. Negative 5 would put me left 5, up 7. Right about there. That's definitely a no. 5, 3 would put me to the right 5, up 3. That's only shaded in the slanted one direction, not both, so that's out. And then negative 7, negative 2 puts me right there, also out. So the only one that works in that scenario is that first one. All right. Take a moment. If you're at home, pause the video. If you're not at home and you're in my classroom with a substitute, my sub will please pause the video right here. But take just a minute and check these in Desmos. Find your solutions to both of those systems. And then once you've had enough time to do that, come back, unpause the video, and see if you were correct. All right, hopefully you had enough time to work this one, or these two. On that first one, you should have gotten answer choice 4, 2, comma, -2. And on the second one, you should have gotten answer choice 2, 2, comma, 0. If you chose 3, 3 is the point of intersection, but a dashed line goes through there, so that was not the point of, or the overlapping area for this. All right, that finishes up this lesson for you guys. So if you will, submit those notes, and then there's a short graded practice assignment for you to do. On the graded practice assignment, pay attention to whether they're asking you about a solution to a system of equations, which is that single point where they cross, or the solution to a system of inequalities, which is any point in that shaded area. Equations don't have shaded areas, only inequalities do. So you want to pay close attention to that when you're working those 10 questions out. Y'all have a beautiful day. Thank you.